Today we'll continue our study of Markov chains and link it back up with Bayesian statistics. To start, remember that last time we looked at this Markov chain. So as a reminder, what we mean to communicate with this diagram is the idea of a random walker moving around on this 4-element state space. So if it's at B, it moves to C with probability a half and to A with probability a half. Then once it gets to its new destination, it follows the arrows there. It might stay at A for one more step, or it might go to B, each with probability a half, and so on. So intuitively, it makes sense that the walker would spend more time at, say, A than at D. So we might want to know, in the long run, what proportion of its time does it spend at each of these locations. And it turns out to be much easier to think about this in a slightly different variation. Suppose we take a large number of steps, in this case maybe 100, and then we ask, what's my probability at that 100th step when I look down at where I am that I'm at A versus B or C or D? So we'll get a probability distribution over this 4-element state space, which says how likely we are to be in each state at the 100th step. So that's going to require that we start somewhere, and we're actually going to generalize the idea that we brought up last time and suppose that we choose our initial state randomly. So we'll call that vector nu. It's a row vector whose entries sum to 1. It specifies the probabilities that we use to choose A, B, C, or D as our starting location. And part A asks us to show that if we multiply nu on the right by p, then we get a probability distribution describing our probability of being in each state at the next time step. So for example, suppose nu is equal to 0.2, 0.4, 0.1, 0.3. So I'm saying I'm going to choose my state according to this distribution, and I want to know after I take another step, incorporating this randomness as well as the randomness of the step, what are my probabilities of being in each state? So for example, my probability of being in state C after one step is going to be the probability that I started at A and then went to C on that step, which is going to be 0.2 times 0 since I can't step from A to C in one step, plus the probability that I started in B and then happened to step to the right, plus the probability that I started at C and then performed a loop step, plus the probability that I started at D and took a step to C. And if you think about it, this is just the dot product of nu with the third column of the matrix P, and that's just the third entry of nu times P. And likewise, the probability of being in state B after one step is going to be the second entry, and so on. So in general, the vector that tells us the probability of being in each state is just nu times P. So if we think about the lesson we learned last time, and this is just another visualization of it, the idea of the stationary distribution is that once we're there, it's not really changing anymore. So like if we start in state 1 and then start taking steps and ask what are our probabilities of being in each of these states, then it fairly quickly stabilizes to this 4 ninths, 2 ninths, 2 ninths, 1 ninth value that we discovered last time. And then it changes so imperceptibly even when n is only, say, 20, that it really looks like the same graph each time. And suppose we change the starting state here, just to reiterate the lesson from last time, we start in B initially. So early on we're getting different distributions here, but then it shakes out to the stationary distribution quite quickly. It's the same one regardless of where we start. But the crucial point to make is that the stationary distribution has the property that when we hit it with P, we update our current state probabilities to account for another step. It doesn't actually change. So here we're asked to use this observation to write down an equation that the stationary distribution should satisfy. And it should satisfy our distribution now is equal to our distribution one step from now. And this equation is almost the eigenvector equation, except we're multiplying the vector on the left rather than the right, and this is called the left eigenvector. Or you can think of it as an eigenvector of P transpose by transposing both sides of this equation. And the eigenvalue here is 1. We multiply P by nu, and we end up with 1 times nu. And there's a very nice theorem in linear algebra whose proof we're not going to go over. It's called the Perrin-Frobenius theorem, and it essentially says under certain conditions, everything works out. This matrix P is going to have exactly one left eigenvector with eigenvalue 1, and all of its entries are going to have the same sign, so we can choose them to be positive. And furthermore, that eigenvector is what you get in every row when you raise P to successively high powers and let that exponent go to infinity. And the condition this theorem requires, aside from ones that are going to be satisfied automatically in our context, is that some power of the matrix has all positive entries. So for example, with this P, we can compute that P cubed still has a 0 entry in it, but P to the 4th has all positive entries. And to interpret that fact in the Markov chain context, what we need to do is remember that the ijth entry of P to the n is the probability of being in state J after n steps starting from I. So we showed that last time, but you can also show it using the result that we just proved by considering a starting distribution nu that's concentrated at a single point. In any case, this condition that some power of the matrix has all positive entries in the Markov chain context boils down to the idea that there's some number of steps such that you can get from any state to any other state in exactly that number of steps. So for example, you can convince yourself that 4 has that property for this Markov chain. Like if you're at A, you can be at A 4 steps later by just taking this loop 4 times. You can be at B 4 steps later by taking it 3 times and then 1 step to B, and so on. You can go through all 16 pairs of states here and convince yourself that in exactly 4 steps you can get from one to the next. And we know that's true because we calculated p to the 4th and we got all positive entries. So what is the point of this Markov chain stuff? Well, suppose we wanted to sample from the distribution 4 ninths, 2 ninths, 2 ninths, 1 ninth. Problem 1 gives us a way to do that. We can set up this Markov chain, start somewhere, and then running the Markov chain for a few dozen steps. It isn't exact, but it will be very close. But on the face of it, that seems a bit ridiculous. We could certainly sample from any distribution on 4 elements we like just by partitioning up the unit interval into suitable length intervals and choosing a uniform random number and deciding which interval it falls in. Furthermore, it seems much more complicated to involve all of these other numbers, these transition probabilities. That's 16 numbers we have to come up with describing the desired distribution. So if you imagine the situation gets much more complicated, like the space that we're sampling over has 2 to the 100 elements instead of just 4, then the objection about having some easy alternative way to sample seems less relevant. We're not going to be able to feasibly snip up the unit interval into that many super tiny pieces. However, the second problem seems to get worse. If we have a desired stationary distribution on an enormous space, how could we possibly come up with a set of transition probabilities that gives us exactly that distribution as our stationary distribution? And that objection also has an answer. We can apply an idea called the Metropolis-Hastings algorithm, which essentially gives us the appropriate transition probabilities for any distribution that we want to sample from. So the way it works is that we have a transition matrix that we're going to call Q. It's called the proposal transition matrix. You can think of Q like a referee. It's just directing traffic. And ultimately, it will be important to choose a good Q, but the algorithm does technically work regardless of the Q that we use, as long as it satisfies some basic properties, one of which is symmetry. So we're going to require that Qij is equal to Qji. And it needs to get around the space. For example, we could require that some power of Q have all positive entries, although that assumption can be relaxed in some cases. So here's how it works. Just like we usually do with a Markov chain, we start in some location, and then this transition matrix Q proposes a new move, which we'll call X proposal. But then rather than just taking that step to the new X, the random walker is going to decide with some probability whether to take that step. And that's where the desired limiting distribution comes in. So suppose that f is specifying the probability mass function of the desired limiting distribution. We'll check the probability mass at the proposed new state as well as at our current state and decide whether to take a step based on that. So if the probability mass is bigger, we're definitely going to take that step. And if it's less, we still might take that step, but just with a probability of that ratio. So this implicitly specifies a new transition matrix P that accounts for Q as well as these ratios. So this ratio of the densities at the proposed state and the old state is called the acceptance ratio. So let's work out the set of transition probabilities we would get for this 4-element state space and the same stationary distribution we had above, 4 ninths, 2 ninths, 2 ninths, 1 ninth. And we'll get to see, do we get the same transition probabilities? Do we get different ones that have the same stationary distribution? Let's check it out. So for our proposal distribution Q, let's just use a nearest cyclic neighbors walk. So from each state, our proposal will either suggest to go clockwise or counterclockwise around this circle, one step. We could consider other distributions Q, but you have to settle on a Q. Let's just use this one. So our desired limiting distribution is 4 ninths, 2 ninths, 2 ninths, 1 ninth. And let's imagine simulating a particular run of this so that we see what's going on. Suppose we happen to start at A, and then the proposer looks at Q and says, let's move to B with probability a half and to D with probability a half. And let's say the proposer happens to choose B. So then the random walker looks ahead at B and says, the desired distribution there only has a mass of 2 ninths. And where I am, I have a mass of 4 ninths. So I'm only going to take that step with a probability equal to that ratio, which is 2 ninths over 4 ninths, which is a half. So the random walker flips its own fair coin and decides, I'm not going to take that step this time. Then the proposer makes another proposal. Maybe it happens to choose B again. The random walker flips its own coin again, and this time it decides, let's go to the proposed state. So the proposer now suggests A or C with equal probability. Let's say it chose C. And the random walker looks ahead and sees the ratio of the desired density where I'm going to where I am is 1. So with probability 1, I'm going to accept that proposal and move to that state. And so on. We just repeat this process of getting a proposal from the proposal distribution and then either accepting or rejecting with an acceptance ratio equal to the probability mass at the proposed state divided by the probability mass at the current state. So let's work out the transition matrix P that we get from this. So if we start at A, the probability of getting to B on the next step is equal to a product of a half, which is the probability B is proposed, and another factor of a half, which is the probability that the proposal is accepted. So that's 1/4. The probability of being at C after one step is 0 because that can't be proposed. The probability of being at D after one step is equal to a half times the ratio, 1/9 to 4/9, which is a quarter. And the probability of staying at A will be 1 minus the sum of those two probabilities, which is 5/8. We could have computed that directly as a sum of the probabilities of rejecting the two possible proposals. And notice that for B, we always accept the proposal, since the two possible proposed states have a desired probability mass that's greater than or equal to the value at state B. Therefore, this row is just the same as Q. Continuing in this way, we can compute the rest of the entries, and they look like this. So notice we did get a different transition matrix this time, but that's no big deal. It shouldn't be surprising that there are different transition matrices that give rise to the same stationary distribution. But let's check numerically that we do get the desired limiting distribution in this case. So this was the P that we came up with, and if we raise P to the 100th power, which tells us the probability of being in state J, given that we started at state I 100 steps ago. And this checks out. We get our 4/9, 2/9, 2/9, 1/9, just like we wanted. We can also visualize this the same way we did above and see that no matter where we start, the probability distribution describing our probabilities of being in each state after n steps converges as n goes to infinity to this desired distribution, where these two are twice as tall as this one, and this first one is twice as tall as each of these two. So that small example was intended to help build some intuition, but it's also really important to see where Markov chains give us something new. So we'll look at this somewhat contrived natural language problem. Although it is quite close to some actually practical algorithms, I've put a reference here to this paper called Markov Chain Monte Carlo Revolution, where Percy Diaconis describes using this algorithm to decipher an intercepted encoded prison note. So here's the setup. Our state space is going to be much, much larger than 4 this time. It's going to be, let's say, the set of tweets, and for simplicity, tweets that just consist of letters. And actually, let's say letters and spaces. So this space is really huge. If we were looking at 1 character tweets, there would be 27 possibilities, 1 for each letter and then the space. If we were looking at 2 character tweets, we would get 27 squared. 27 choices for the first position, 27 for the second position, and then the product property of counting tells us that we multiply those to get the total number of length 2 strings, so that's 27 squared. We're considering the full character limit, which is 280, so we're going to have 27 to the 280 elements in this space. So we're definitely not going to be able to get a hold on this space by representing the whole thing at any point. But notice that the Markov chain approach does get around that. We can start somewhere in this space and just move around, as long as we have some way to move around locally. And if we follow Metropolis-Hastings, then for whatever probability distribution we're trying to sample from, we will get there eventually. So there are lots of ways you can come up with a probability measure that's somehow intending to reflect actual natural language structure. Here's a very simple one. What we do is consider every pair of letters, and we ask, how likely is it that we'd see those 2 letters back to back, based on how frequently that happens in the English language at large. And then we multiply all those ratios across the whole tweet. So consider a message like, "Hi there." We'll ask ourselves, for what fraction of 2-letter sequences in the English language is it the case that the 2 letters we get are H and I? And I don't know what it is, so I'll just make something up. Maybe it's 0.008. Then we'll ask, what about I comma space? Maybe that one's 0.002, because it is relatively uncommon for words to end with I. Then we'll take the next pair, and so on, and then we'll just multiply all these values. So notice we're going to get an extremely tiny number, but that's okay because at the end we'll say we just want the probability associated with the given tweet to be proportional to this product. So every point gets a really tiny number, but still the ones that are more plausible will end up with a higher product than the ones that are implausible. So this is a very common way of specifying a probability measure on a very large space. We come up with some sort of score and we say we want the probability to be proportional to this. So the actual probability is going to be that value divided by the sum of all those values over this really huge space. So we're never going to be able to compute that denominator. We're going to have to be able to work with just those values that we want the probability to be proportional to. So part A says, how should we deal with tweets that are less than 280 characters? We can just pad them out with spaces. There are probably better ways to handle that, but that's one simple one. So consider all the characters after the last one to be spaces all the way to the end. How can we estimate G in practice? We could just download a bunch of tweets and just compute the proportions. For each tweet, we loop through the tweet, we consider each pair of characters we see, and we just bump the count by 1 for that particular pair. So we're just doing a tally for all 27 squared pairs, and we'll want to do some pre-processing to get rid of things that aren't letters, lowercase, uppercases, and things like that. Okay, and part C is the rub. How do we actually generate a random tweet drawn from this probability measure? Hopefully this example will be convincing that Markov chains are giving us something new, because this task kind of seems hopelessly impossible. We have this probability measure specified in a way that doesn't even allow us to calculate any probabilities. We can just calculate ratios of probabilities between different tweets. And also the space is so large that any algorithm that involves all of its elements is entirely infeasible from the outset. Nevertheless, the Markov chain machinery we've developed, specifically the Metropolis-Hastings algorithm, gives us a very nice solution. So we'll just start somewhere in the space. It's probably worth figuring out how to start somewhere good, but just for simplicity, let's start somewhere, like the string of all A's. So you have 280 A's. As a point in the space, that's where we're going to start. Now we need a proposal distribution. And here's where it becomes relevant to have a proposal distribution that's easy to deal with. We're going to need to make a lot of proposals, so it should be something really simple. And one simple thing we could do here is just pick a random position and just change the character in that position to a new character chosen uniformly at random from the 27 possibilities. So let's say the proposer happens to choose the third position and propose that the letter there be switched to an H. We have to decide whether to accept this proposal, and that's where the desired limiting distribution comes in. We just need to compute the ratio of the probability mass at this new state to the probability mass at our current state. So the acceptance ratio alpha is going to be equal to the ratio of the scores that we have for these two tweets. That's true even though the scores are only proportional to the actual probabilities, because the denominators are going to be the same. And notice that the vast majority of these factors cancel, which is fortunate because otherwise we might be dealing with underflow issues. And what we end up with is just this ratio involving 4 lookups from the proportion dictionary we tabulated when we processed all those tweets we downloaded. So that's it. We start somewhere in the tweet space. We pick a position between 1 and 280 uniformly at random, and then also a new character uniformly at random from the 27 possibilities. And then we actually make that proposed change with probability equal to the ratio of the factors that that change affected. And then we just repeat this update many times. And after sufficiently many steps, Metropolis-Hastings says that the distribution that describes where we are in the tweet space is actually going to be approximately proportional to this plausibility score we have for each tweet. So in this problem, we'll tie the Markov chain stuff together with the Bayesian statistics by looking at a situation where the distribution we want to sample from is a Bayesian posterior distribution. So this is going to be a Bayesian linear regression model, and what we'll see is that the parameters of our model, the slope and intercept, are going to get distributions rather than fixed values as in frequentist statistics, consistent with the fact that we're treating them as random variables. So our model is going to be y equals mx plus b plus epsilon, where epsilon is normally distributed with mean 0 and variance, let's say, 0.05 squared. We need Bayesian priors for m and b, and we'll just take normal distributions with mean 0 and variance 100. So it's very flat. We're trying not to have too much influence on the final result. So for our simulated data, let's use a slope of 0.4 and an intercept of 0.2. We get something that looks like this. And we want to interpret all of these data points as evidence to update those priors and get a posterior. So remember that posterior is proportional to likelihood times prior, and the likelihood associated with a particular collection of observations is going to be proportional to the product of epsilon's Gaussian densities evaluated at all of the epsilon values associated with these xi's and yi's. We're not going to want to have to multiply this by the prior and try to come up with a way to directly sample m and b from the posterior. Instead, what we'll do is apply Metropolis-Hastings to likelihood times prior and start somewhere in MB space, perform Metropolis-Hastings updates many times, and that will give us a sample from the posterior distribution. Then we can do that whole process many times And we'll get lots of observations from the posterior, and from that we can draw conclusions about the posterior distribution, like the variance of M or the variance of B, quantiles, means, and so on. So let's code this up. Let's start with our normal distribution, mean 0 and standard deviation 10. This is the prior distribution for both M and B. Let's begin by defining a quantity we'll call delta, which takes the vector of x's and the vector of y's, as well as a particular M, B pair. And it works out the exponent of this expression we just came up with. Then we'll compute the actual acceptance ratio based on that. So we'll need an M and B, which is currently where we are, as well as a proposed M and a proposed B. And we'll just calculate that ratio. And we also need to account for the ratio of the priors. And here we won't do anything analytical. We'll just defer to the PDF function from distributions. So to see that this function is doing something plausible, let's look at the acceptance ratio for a pair of values that's very inconsistent, like 0, 0. The slope and an intercept of 0 are very inconsistent with the data, while 0.4 and 0.2 are spot on. And we get this completely enormous ratio, 1.8 times 10 to the 37. So that makes sense. Next, let's actually perform the Markov chain for n iterations. So we'll start somewhere. Let's say M, B is equal to 0 and 0. And then we'll keep track of the parameters for each iteration. And then we'll repeatedly update. So we'll come up with a proposal. And then we'll accept it with probability alpha. And if we do accept it, we'll push it to our running list of thetas. And finally, we return this list of thetas. So we're keeping track of our whole history. So let's run it for 3,000 steps. Now let's see what's up. So we start here at 0, 0, and then after a few hundred steps, we start to get pretty close to the region where we would imagine the posterior mass is concentrated. And then we continue to fluctuate quite significantly at that point. And these fluctuations are stemming from the fact that M and B are still random. They still have a distribution. We're not getting a specific value. We're getting a whole spectrum of possible values. But they're mostly concentrated around the ordinary least squares solution. But notice here that we could get some error bars on, let's say, the slope by running this many times. So we see that the posterior distribution on M and B's is indeed centered at 0.4, 0.2. But interestingly, M and B are negatively correlated in this posterior distribution. And note that we could use the observations for M to come up with a variance. We could just compute the sample variance for the x values of these points, and likewise for B. So in summary, today we learned the Metropolis-Hastings algorithm. Given a set omega and a desired distribution specified by a PDF or PMF f, we can sample from that distribution by starting somewhere in omega, then moving to a new state proposed by a given fixed proposal distribution with probability equal to the ratio of the mass or density at the new state to the mass or density at our current state. And if that ratio is bigger than 1, then we just definitely take that step. And then we repeat this whole process many times, and Metropolis-Hastings says the limiting distribution of our location as the number of steps goes to infinity is equal to f. And Markov chain Monte Carlo refers to using Markov chains to sample from distributions for purposes of computing various integrals like means, variances, quantiles, and so on. And this is especially helpful in Bayesian statistics because we often have posterior distributions that are hard to deal with analytically, but for which we can use Markov chains to sample. And then we can estimate posterior means. With an average of that posterior sample, we can estimate variances and quantiles, similarly using sample variances and sample quantiles for the results we get from the Markov chain sampling.